This is our dipole antenna. This is the second phase of a dipole antenna. So this is the paper we are following. So what we thought is that according to the um, like yeah, according to the abstract, we have to design a 28 gigahertz dipole antenna. So as I've told earlier, the equation is very simple. This is the equations we're using. So we have the wavelength equal to c by f. So you have to find the wavelength where c is the velocity or the velocity of the em wave, which is 3 into 10 raised to 8 meter per second. And the frequency will be what we want now, that is 28 gigahertz. 28 into 10 raised to 9 hertz. So when you divide that, you will get wavelength. So then you can see from here the dipole antenna has current distributions for length. You can have the length of the dipole antenna can be lambda by 2, lambda by 10, or anything. So we can take it as lambda by 2, which is like half wave. It's called as half wave dipole. We can take the length as lambda by 2. So the length will be lambda by 2, and the rest of them are same. That feeding gap will be length by 200 and radius will be length by 1000. Rest of them are same, but length we are taking it as the half of the wavelength. Okay, length we are taking it as half of the wavelength. Rest of them are same. Okay, so these are the equations which we get, the design equations of dipole antenna. So as usual, to design any antenna, you need three parameters. First one is the resonant frequency, which is 28 gigahertz, and second one, which is the like uh, what is the dielectric constant, right? What is the dielectric constant, and what is the height of the substrate and all that. So here, as it is dipole antenna, it's we don't need all that because we don't have a substrate as such. What we are having is, you have like two. I'll just zoom this, then you will understand. So when you just zoom this out, see, this is the dipole. So you have, this is the one pole, and you have another pole, and in between that you can see that there is something here, right? So this is the gap. So you have a here you have a pole, and here you have a pole, and here this is a gap which is covered with vacuum. Okay, so this is what you just like how you can see in this yeah. See, just like how you are seeing in this one will be a pole. So you have some insulator here, right? So this is a pole, and this is a pole, and here you have an insulator. So we also have two poles and insulator. Insulator is our vacuum. Okay. So now let's go to the design part. So this also I have explained before. So whenever you're designing an antenna, there are some steps you have to follow. First, you have to design the design itself, like the material, the parts you have to design. You have to give the materials. You have to give the gap and all that. So you have to design the material, and after that, you have to have a, after the designing physical design, you have to give the boundaries. You have to give excitation, and you have to give the sweep, that is the analysis step. So there are four things you have to do: design, boundary, excitation, sweep. And then you can validate your model and simulate it, right? So first, here let's start with the dipole. So you have two dipoles here, two monopoles. Like you have two, one this one, and another in the downside end you have one more. Yeah. So first you can design that. So this is the dipole. You can also see, yeah, you can see that this is the height of the this is the height, this is the radius and all that. It's like a cylinder. It is generally the dipole, it is basically like a cylinder. So you need the height and the radius. So you can see this is the radius and this is the height. So here you will get this dipole. And after that, what we can do is like instead of making like two different monopoles and then giving a gap. What I am doing is I'm making the whole thing first. This is the whole thing will be like one cylinder, and after that I am just cutting out this gap, just like how we did in the first phase. I'm making the whole cylinder and I'm cutting out the small gap. The gap is, this is the gap. See, you can see this is the gap. So the gap is like its height is 0.02, is very small gap, and it has a radius same as the conductor radius. It has the same radius, and after that you can see that this gap I'm subtracting. So this is the dipole, I'm subtracting this gap from the dipole. So here, this portion, the orange portion you can see over here, this is actually the gap, this is actually the vacuum. So the whole thing was one conductor, and I'm cutting out a part of the conductor and throwing it away. And here I am actually having vacuum, I'm putting vacuum inside this. This will act as an insulator between the two poles. Okay, that will create a dipole. Okay, similarly the conductor we are giving, you can see that if you just double click, you can see the material I'm given it as PEC is perfect electric conductivity. Okay, so it is a perfectly conducting material. That is what we call it as PEC. Okay, so you can see that both the this pole as well this conductor as well as this conductor, both of them are perfectly conducting, and in between them you have vacuum which act as an insulator kind of thing, right? So after this, you can see that there is a kind of sheet inside this, right? This one, like if you can just click it, you can see that. Yeah, you can see that there is a kind of sheet inside this gap. So what we are doing is, you have two conductors, you have a gap, and I am putting a sheet kind of thing. This is called a port. So inside through this port, I am giving it the supply. So let's see, if you consider this. Yeah, if you consider this, so let's say this is our conductor and this is our another conductor, and this is where you have the vacuum. So I am actually inserting a port here, so that I can, this is like this is a cable, right? So here I am actually giving it the input. So the input will come like this, and it will spread through the conductors. So this, in the middle of the conductors I am giving the input, right? So that is what I'm shown here. So this is a lumped port, and you can give the input here. Right, this is actually the construction of this antenna is very simple. These are the constructions of the antenna, and after that, after all the constructions, you have to do this also. After all the construction, you have to have a radiation bound. This big cylinder you see, this is called as a radiation box. So you have to have a radiation box, otherwise you won't get the radiation patterns of the antenna. So after this is the design part. So in the designing part, what we are doing, we are having a conductor, right? We are building a big conductor, and you're taking a piece between, like a gap, you're creating a gap between, you're cutting the conductors and creating a gap between them. That is simple. And after that, you are having a port inside the gap where you can have the input signal, and you have a radiation boundary. So these are the very simple construction of dipole antenna. And you can see whatever, yeah, these are the height, radius, whatever dimensions I have used, this I have put it here. And the dimensions of the conductor and everything, it comes from, I have already explained you before, it is coming from this, where length is lambda by 2, and length is not 143 by f. I have taken length as lambda by 2, which is half dipole, like half wavelength. So L equal to lambda by 2, and after that you can get gap as well as radius and everything. Okay, so after that, the second part which we have to see is providing boundary conditions. So for boundary conditions, first for the radiation box, you can provide just right click, assign boundary, you have radiation, right? So this is the radiation box boundary. So you can see in this project manager, you can see boundaries. There are two boundaries. First one is radiation boundary, which is this thing, and then is perfect E, that is for the conductor, that will be inside this. Okay, so that will be inside this boundary. Just a minute. Yeah, if you see this perfect E, if you go inside, you can see that it is here. See, you can see the boundary conditions in this conductor. So this is the gap. You can see the gap also, right? So this is perfect. So why we are giving boundary conditions? We have to make the software understand that this conductor is conducting, right? It is conducting or it is radiating. We want to make the software understand. That is why we are giving the boundary conditions. So we have given two boundary conditions, first for the air radiation box and second is for the conductors. So conductors has to be perfectly conducting. So I'll show you that. This is a conductor, just assign boundary and perfect. Okay, so I'm not doing any changes here because this is a simulated model. I cannot make any changes here, right? And after that, you have vacuum. You don't have to give any boundary conditions, just a vacuum. Okay. Now, after boundary condition, you have to give excitation. So you can see that I have given excitation to the port, which is inside this or in between the conductors. So you can see that this is the port P1. So here just you can right click, you can give assign excitation lumped port. If you click that, it will assign, you can give the like excitation. Okay, so what I've discussed till now is that you have three steps. First is designing. So I have discussed the designing part and how the equations came and all that. It's very simple design. And second, I have told you which parts we are giving boundaries. Second one is boundary condition, third one is excitation. After all three, you have to go for analysis. So in analysis, you have to give the sweep. Sweep will be like 20 to 35. Why I have taken 20 to 35 is that you have 28. We are designing an antenna for 28 gigahertz, right? So you have to have this resonant frequency between the sweep. The 25 and 30, 35 covers 28, right? So whenever your so what happens when you're simulating the model, the software will start like step by step, it will start giving. So let's say you can also see the display, you can see that the first step is 20, 20.1, 20.2. So the software will give all this frequencies to the antenna, and it will see in which frequency the antenna is giving the proper radiation or resonating when the antenna is resonating. So it can be seen that in that near 28 gigahertz the antenna will resonate, right? So to check that, we are giving the sweep. So after giving everything, after giving sweep and everything, you have to validate your model. So if you validate your model, you can see that everything is tick or correct. So if your model has any like red color wrong mark, it means that your model is not correct. So now our model is having everything correct. So this is called as a perfect model. So the model has no problem. The model is validated. After that, you have to analyze all that. Okay, I have already analyzed it. So you have to analyze, and when you check the result, you can see that your antenna is resonating for 27.5 gigahertz, which is good. 28 means 0.5 gigahertz is fine. You have we are our antenna is resonating at desired frequency, which is 27.5 gigahertz. So there is also other plots. I have also plotted all the other plots here. So this is the VSWR, which is also less in 27.5 gigahertz. And you have radiation pattern. So this is the radiation pattern, and you have a 3D polar plot also, which is this. So you can see this is the 3D polar, sorry, just a minute. Yeah, 3D polar plot. So you can see that wherever the red comes, it is giving high radiation. So our antenna is giving radiation throughout 360-degree. You can get the radiation. Okay. So this is basically dipole antenna, which is resonating for 28 gigahertz. Thank you.